Welcome everyone. Today we're diving into Chapter 6, Networking in Java. This is part of our advanced programming series. I'm excited to guide you through this fascinating topic. We'll explore how Java handles networking, covering key concepts and practical techniques. So let's get started and see what's ahead in this presentation. Let's take a look at the contents of this section. First, we'll explore how to connect to a server, which is fundamental for any network communication. Then, we'll move on to implementing servers in Java, giving you the practical skills to create your own server-side applications. Next, we'll cover sockets, ports, and URLs. These are the building blocks that enable communication over a network. Understanding these concepts is essential to grasp how data flows between clients and servers. Throughout this presentation, we'll see how all these pieces fit together to build robust networked applications. So, let's dive into each of these topics and see how they connect to the bigger picture of network programming. Welcome to this slide on introduction. Java offers a wide range of built-in networking capabilities that make it quite straightforward to develop both internet-based and web-based applications. Now, when we talk about network programming, we're referring to writing programs that run across multiple devices, computers, that are all connected through a network. This connectivity allows these devices to communicate and share data seamlessly. In Java, we can leverage the classes in the JavaNet package to facilitate this communication, whether it's over TCP or UDP protocols. With TCP, Java provides stream-based communication, which treats data as continuous streams, similar to reading and writing files, making data transfer reliable and ordered. On the other hand, UDP offers packet-based communication, which transmits individual packets of data. This is particularly useful for sending images, audio, or video, where speed is often more critical than perfect delivery. Both approaches are essential tools in our networking toolkit, and understanding them helps us build versatile and efficient network applications. Let's continue with the concept of sockets. So, a socket is essentially a way for computers to connect and communicate with each other. Think of it as a software construct that represents one endpoint of a connection. It's like a door that allows messages to flow between applications. A socket is host local, meaning it's created on a specific computer, and it's managed by the operating system. It's an interface created by the application that controls how data is sent and received. When two computers want to talk, each side opens a socket. Now, just like you identify a file by its name when opening it, you identify a computer when connecting to it by its IP address. That unique address makes sure your messages go to the right place. There are actually two main types of sockets, which we'll explore further. But for now, remember that sockets are fundamental for network communication, serving as the doors through which data flows. Now, let's take a closer look at stream sockets. With stream sockets, a process establishes a direct connection to another process, allowing for a continuous flow of data between them. Think of it like a phone call. Once the connection is made, the conversation can go back and forth seamlessly. Because of this, stream sockets are said to provide a connection-oriented service, meaning they set up a dedicated communication channel beforehand. The protocol that's commonly used here is TCP, or Transmission Control Protocol, which ensures reliable delivery, proper sequencing, and error checking. On the other hand, we have datagram sockets. These work a bit differently. Instead of maintaining a continuous connection, datagram sockets send data in individual packets or datagrams. This is similar to mailing letters. Each packet is sent independently, without a dedicated connection. The protocol used here is UDP, or User Datagram Protocol, which is connectionless. That means it doesn't guarantee that packets will arrive in order, but it allows for faster transmission and less overhead. Understanding these differences is crucial because it influences how we design network applications, aligning with the overall goal of efficient and reliable data communication. Let's talk about ports. Ports are the way we connect to specific programs on other computers over a network. Think of each port as a unique number that helps us identify exactly which program we want to communicate with. Since computers often run many programs at once, we need a way to specify the correct one, and that's where port numbers come into play. Some programs, especially common networking services like Telnet, FTP, and web services, always use the same port numbers. These are known as well-known ports. For example, Telnet operates on port 23, FTP on port 21, and web services on port 80. This consistency makes it easier for networks to communicate effectively, knowing which port to target for a specific service. Understanding ports and their numbering is fundamental to grasping how computers coordinate and communicate over a network, ensuring that data reaches the right application on the right machine. Let's talk about socket programming using TCP. A socket, in essence, is like a door that connects an application process to the end-to-end transport protocol, which could be UDP or TCP. When we're focusing on TCP, it provides a service that ensures the reliable transfer of bytes from one process to another. Now, this process, meaning the actual data transfer, is controlled by the application developer, giving us the flexibility to design how our applications communicate. At the same time, the operating system plays a crucial role in managing the underlying network operations, acting as the intermediary that handles the actual transmission over the network. Think of the host or server as the destination where the data is headed, also managed by the operating system. So, in summary, socket programming with TCP involves a collaboration. The application developer defines the processes and data flow, while the operating system manages the transport and delivery across the internet. This setup is fundamental for building reliable networked applications that need guaranteed data transfer. Let's talk about socket programming with TCP. First off, the client needs to contact the server, but of course, the server process must be running beforehand. Think of the server as having a socket, kind of like a door, that's always ready to welcome incoming connections. Now, when the client wants to connect, it creates its own local TCP socket. This involves specifying the IP address and port number of the server process, so it knows where to go. Once the client creates this socket, a TCP connection is established between the client and server. On the server side, when it receives a connection request from the client, it creates a new socket specifically for communication with that client. This is a key point because it allows the server to handle multiple clients simultaneously. It's like opening a new line of communication for each client, and it uses source port numbers to keep track of which client is which. This mechanism ensures efficient, multi-client communication, which is fundamental to building scalable network applications. It's all about establishing reliable, organized channels for data exchange. Let's take a closer look at how the client and server establish a connection using TCP sockets. First, the server waits for an incoming connection request, meaning it's in a listening state, ready to accept a client. When a client attempts to connect, the server accepts the request with the accept call, which creates a new socket, often called the connection socket, dedicated to this specific client. On the client side, it creates a socket and then connects to the server's host ID and port number. Once connected, the server can read the request sent by the client through the connection socket and then write a reply back to the client, completing the communication cycle. This process is part of the TCP connection setup, which ensures a reliable, ordered, and error-checked delivery of data. The key takeaway here is that the server is always in a listening mode, waiting for connection requests, and when a client connects, a dedicated socket is created to handle that specific interaction. This setup allows for smooth, reliable communication between client and server in networked applications. In this slide, we're looking at a practical example of socket programming using TCP, which is a core concept in network communication. So, imagine a simple client-server application where the client starts by reading a line of input from the user, which we call in from user. This line is then sent over the network through a socket, using the out-to-server stream. On the server side, it reads that line directly from the socket connection. Next, the server processes this input by converting the line to uppercase, which is a straightforward way to demonstrate data manipulation. After this transformation, the server sends the modified line back to the client via the socket. When the client receives this response, it reads the data from the socket through the in-from server stream and then prints out the uppercase version of the original input. The key points here highlight how TCP socket communication enables a continuous exchange of data between client and server, supporting real-time interactions. This example illustrates the fundamental steps involved: reading user input, sending data over a socket, processing on the server, and sending back a response. It connects to the broader theme of network programming by showing how data flows reliably and efficiently between two endpoints, which is essential for building interactive network applications. Let's take a closer look at this example of a Java client using TCP. First, we import the necessary classes from java.io and java.net to handle input-output streams and networking functionalities. The main class here is TCP client, which contains our program's entry point. Inside the main method, we declare variables to hold the message from the user and the modified message received from the server. Next, we create a buffered reader called InFromUser, which reads input from the console. This allows us to get user input easily. Then, we create a socket object named ClientSocket, connecting to a server identified by hostname on port 6789. This step is crucial because it establishes the connection between the client and the server. After that, we set up an output stream, out to server, using data output stream attached directly to the socket's output stream. This stream is used to send data from the client to the server. The overall flow shows how we create the input stream, connect the client socket to the server, and then create the output stream attached to that socket. This example illustrates the fundamental steps of setting up a TCP client in Java: establishing a connection, creating input-output streams, and preparing for data exchange. These concepts are key to understanding how client-server communication works in network programming. In this slide, we're looking at an example of a Java client using TCP to communicate with a server. First, we create a buffered reader called InFromServer, which is attached to the socket's input stream. This allows us to read lines of data coming from the server efficiently. Next, we see the line where we read input from the user with InFromUser read line. This is the message the user wants to send to the server. Then, we send that message to the server using out-to-server write bytes, appending a newline character to indicate the end of the message. After sending the message, we wait for a response from the server by reading a line with InFromServer read line. This is stored in modified sentence. Finally, we print out the server's response with system out println prefixed by from server. And at the end, we close the socket with client socket close, which is important for cleaning up resources. The key takeaway here is how we create an input stream attached to the socket, which enables us to receive data from the server, and how we send lines of text back and forth to facilitate communication. This example illustrates the core flow of a TCP client in Java, connecting input and output streams to handle message exchange smoothly within the overall client-server architecture. All right, let's walk through this Java server example that uses TCP. First, we import the necessary classes from java.io and java.net packages, which handle input-output streams and networking functionalities, respectively. We define a class called TCP server, and inside the main method, which throws a generic exception for simplicity, we set up our server. We declare two string variables: client sentence, which will hold the data received from the client, and capitalized sentence for processing or responding if needed. The key step here is creating a server socket object, called welcome socket, that listens on port 6789. This socket essentially acts as our server's welcoming point for incoming client connections. Next, we enter an infinite loop, meaning our server will continually run and accept connections. Inside this loop, we call welcome socket accept. which blocks the program until a client initiates contact. When a client connects, a new socket object, connection socket, is created to handle that specific communication session. After establishing the connection, we set up a buffered reader, InFromClient, attached to the input stream of the connection socket. This allows us to read data sent by the client in a buffered and efficient manner. So the key points here are creating a server socket on port 6789, waiting for a client to connect, and then creating an input stream to receive data from that client. This setup is fundamental for building TCP-based server applications in Java, and it ties into our overall theme of understanding client-server communication. Now, let's walk through this example of a Java server using TCP sockets. First, we create a data output stream called OutToClient, which is attached to the socket's output stream. This allows us to send data back to the client. Next, we read a line of input from the client using InFromClientReadLine. This captures whatever message the client has sent. Then, we convert that message to uppercase and add a newline character at the end, storing it in capitalized sentence. After that, we write this transformed message back to the client using OutToClientWriteBytes. The process is wrapped in a loop. Once we finish sending the response, the server waits for another message from the same or a new client connection. This pattern demonstrates how the server reads input, processes it, and responds, forming the core of TCP communication in Java. Let's talk about socket programming with UDP. Unlike TCP, UDP doesn't establish a connection between the client and the server. There's no handshaking process involved, which makes it simpler and faster. When the sender transmits data, they explicitly include the IP address and port of the destination in each packet. On the receiving end, the server needs to extract the sender's IP address and port from the received packet to know where it came from. One important thing to remember about UDP is that the transmitted data might arrive out of order or even get lost along the way. This makes UDP suitable for applications where speed is more critical than guaranteed delivery. Overall, UDP offers a lightweight, connectionless communication method that's ideal for certain real-time applications, but it requires handling some of the reliability aspects at the application level. Now let's look at how the client and server interact using UDP sockets. First, on the server side, it runs on the host identified by hosted, ready to receive messages. The client creates a datagram that includes the server's IP address and a specific port number, X, which it wants to communicate over. It then sends this datagram via the client socket, which is set up by creating a socket and binding it to the port X on the server side. We have the server socket, which is created as a datagram socket, waiting to read incoming datagrams. Once the server receives a datagram, it processes the message, and then it writes a reply back to the client. When doing so, it specifies the client's address and port number to ensure the response reaches the correct destination. This interaction exemplifies the key principles of UDP communication: connectionless, quick exchanges, and the importance of addressing to direct messages appropriately. It's a fundamental pattern that underpins many real-time applications and highlights the simplicity and efficiency of UDP socket interactions. All right, let's walk through this example of a Java UDP client. First, you notice we start by importing the necessary classes from java.io and java.net packages. These are essential for handling input-output streams and network communication. Next, we define our class, UDP client, and within the main method, which throws an exception to handle any runtime errors. The first important step is creating a buffered reader called InFromUser. This allows us to read input directly from the user via the console. Then, we create a datagram socket, instance named client socket. This socket is what we'll use to send and receive UDP packets. After that, we translate the hostname into an IP address using inetaddress, get by name. This step is crucial because UDP communication requires an IP address, and DNS handles this translation behind the scenes. We also initialize byte arrays called send data and receive data, each with a size of 1024 bytes. These arrays will hold the data we send and receive over the network. The next step is reading a line of input from the user, which we store in the variable sentence. Then, we convert that string into a byte array using getBytes, preparing it for transmission. This example highlights the core steps of setting up a UDP client, creating input streams, creating the client socket, and translating the hostname into an IP address using DNS. These are fundamental concepts that underpin reliable UDP communication in Java and connect directly to the broader theme of network programming. Let's walk through this example of a Java client using UDP. First, we create a datagram packet called sendPacket. This packet is constructed with the data we want to send, its length, the IP address of the server, and the port number, which in this case is 9876. This step is crucial because it prepares the data for transmission over the network. Next, we send this datagram to the server using the client socket's send method. This action transmits our data to the specified address and port. After that, we prepare to receive a response by creating another datagram packet called recevePacket, which is initialized with a buffer for the incoming data. The client then waits for a response from the server with the receive method. When the packet arrives, we extract the data from recevePacket and convert it into a string, which we store in modified sentence. Finally, we print out the response from the server and close the socket to free up resources. This example highlights key steps in UDP communication: creating a datagram with the correct data and destination, sending it, receiving a response, and then processing that response. These steps are fundamental in understanding how UDP clients operate within network programming. Let's take a closer look at this example of a Java UDP server. First, we import the necessary classes from Java.io and JavaNet, which provide the input-output and networking capabilities needed. We define our class as UDP server, and within the main method, we start by creating a datagram socket that listens on port 9876. This socket is the core communication endpoint for receiving and sending UDP packets. Next, we allocate byte arrays for receive data and send data, each with a size of 1024 bytes. These arrays serve as buffers to hold incoming data and prepare outgoing data. The server then enters an infinite loop, which allows it to continuously listen for incoming datagrams. Inside this loop, we create a datagram packet called recevePacket, passing in the receive data buffer and its length. This packet acts as a container for the incoming data. The server calls the receive method on the socket, which blocks until a datagram arrives, storing the data in recevePacket. This setup demonstrates the fundamental process of receiving data over UDP in Java. This example highlights the essential steps: creating a socket at a specific port, preparing buffers for data, and receiving packets. These are key concepts in building network communication using UDP, which is connectionless and suitable for applications where speed is more critical than guaranteed delivery. Now, let's walk through this example of a Java server using UDP. First, we read the incoming data from the recevePacket by converting its data into a string, which gives us the actual message sent by the client. Next, we retrieve the sender's IP address using, and also get the port number with recevePacket getPort. These are crucial because they tell us where to send the response. Then we process the message by converting it to uppercase. This is just an example of server-side processing. After that, we prepare the data to be sent back by converting the capitalized string into bytes. We create a new datagram packet, which contains this data, along with the recipient's IP address and port number. Once the packet is ready, we send it through the server socket using server socket. sendPacket. The process then loops back to wait for the next datagram, allowing the server to continually listen and respond to incoming messages. Throughout this flow, the key points are extracting the sender's address and port, processing the message, creating a new datagram, and sending it back, all essential steps for handling UDP communication effectively. All right, let's walk through this example of a client class in Java. Here, we start with the main method, which is the entry point of our program. Inside the try block, we create a new socket object, connecting to localhost on port 1234. This is the key step where we establish a connection to a server running on the same machine. Next, we set up a buffered reader to read incoming data from the socket's input stream. This allows us to efficiently read text data sent from the server. Now, we print out a message indicating that we're about to display the received string. Then, the code waits in a loop until the input stream is ready to be read, ensuring that we don't try to read before data is available. Once the input is ready, we read a single line from the server using readLine and output it to the console. After that, we print a closing quote and a new line for clarity. Then, we close the input stream to free resources. If any exception occurs during this process, say if the server isn't running or the connection fails, the catch block will handle it gracefully by printing an error message. Overall, this example highlights how a client can connect to a server, read data, and handle errors, which are fundamental concepts in socket programming. It demonstrates the importance of establishing a connection, reading data safely, and managing exceptions to ensure our programs are robust and reliable. Let's take a closer look at this server example in Java. First, notice that we import the necessary packages, including Java, Lang, Java.io, and JavaNet, which provide the core classes for network communication. In the main method, we define a string variable called data, which contains the message we want to send. Here, this is a test MSG. Next, we create a server socket object, binding it to port 1234. This is the port on which our server listens for incoming connections. When a client connects, the server accepts the connection, creating a socket object. Once connected, we print a message indicating that the server has established a connection. Then, we set up a printer to send data through the socket's output stream. We print a message showing the string we're about to send, making it clear what data is being transmitted. After sending the message without print data, we close the output stream and the socket, followed by closing the server socket itself. This ensures proper resource management. Finally, there's a catch block that handles any exceptions. If something goes wrong during this process, it prints a message indicating failure. This example highlights the key steps in setting up a basic server: listening on a port, accepting a connection, sending data, and then closing everything cleanly. It's a fundamental building block for understanding client-server communication in Java, which ties into our broader theme of network programming. Now, let's take a look at some important methods that can really make a difference in our approach. These are key techniques that help us achieve better results and more effective outcomes. First, it's crucial to understand the core principles behind each method, because that's what allows us to apply them correctly in different situations. For example, some methods focus on improving communication, while others are designed to optimize processes or enhance teamwork. What's really important here is to see how these methods connect to the overall theme of our presentation: improving efficiency and effectiveness. By mastering these techniques, we can address challenges more confidently and create more impactful solutions. Remember, the goal with these methods isn't just to learn them, but to integrate them into our daily practice for continuous improvement. Let's take a closer look at the different ways to create a server socket in Java. The first constructor attempts to create a server socket bound directly to a specified port. If that port is already in use by another application, an I/O exception will be thrown, so it's important to handle that possibility. Moving on, the second constructor adds a backlog parameter. This is where it gets interesting. The backlog specifies how many incoming client connection requests can be queued up if the server is busy. Essentially, it helps manage how many clients can wait to connect while the server is handling others. The third constructor further refines this by allowing us to specify a particular IP address to bind to, using an inet address object. This is especially useful when a server has multiple network interfaces or IP addresses, and you want to listen on a specific one. It gives more control over network configuration. And finally, there's the no-argument constructor, which creates an unbound server socket. This approach is useful if you want to set up the socket first and bind it later, perhaps with the bind method once your application is ready to start accepting connections. These constructors provide flexibility depending on your application's needs, whether you're binding immediately, controlling incoming queues, or choosing specific network interfaces. This aligns with the overall theme of building robust, configurable server applications in Java. Now let's take a closer look at some key socket methods. First up, getLocalPort. This method simply returns the port number that the server socket is listening on. It's particularly handy if you set the port to 0 in the constructor, which allows the server to choose an available port for you. Next, we have the accept method. This one waits for an incoming client connection. It blocks, meaning it pauses execution, until a client connects, or until the socket times out if you've set a timeout value with setSoTimeout. If no timeout is set, it will wait indefinitely. The setSoTimeout method itself allows you to specify how long the server should wait for a client during accept. This is useful to prevent your server from hanging forever if no clients are connecting. Lastly, the bind method is used to associate your server socket with a specific address and port, especially when you've created the socket with the no-argument constructor. Connecting all these points, these methods give you control over how your server socket listens, waits, and handles incoming connections, which is fundamental for building robust network applications. Let's take a closer look at some of the key methods available in the socket class. First, the connect method allows us to establish a connection to a specific host and port, which is essential when we create a socket using the no-argument constructor. Think of it as dialing the phone to connect to someone. Next, the getInetAddress method gives us the address of the other computer we're connected to, which is useful for confirming the remote endpoint. The getPort method tells us the port number on the remote machine that we're connected to, while getLocalPort reveals the port on our local machine that the socket is bound to. These details help us understand exactly where our data is flowing. The getRemoteSocketAddress method provides the full address of the remote socket, combining both IP address and port, giving a complete picture of the connection endpoint. Moving on, the getInputStream and getOutputStream methods are crucial. They give us access to the data streams. The input stream is connected to the remote socket's output, allowing us to read incoming data, while the output stream is connected to the remote socket's input, enabling us to send data. Finally, the close method terminates the connection, making the socket no longer usable. This is important for resource management, ensuring we free up system resources when we're done with the socket. Overall, these methods are fundamental for managing socket connections effectively and securely, tying into our broader theme of network communication and resource control. Let's take a closer look at the InetAddress class methods. First, we have getByAddress, which allows us to create an InetAddress object directly from a raw IP address in the form of a byte array. This is useful when you have the IP address data but not necessarily the hostname. There's also an overloaded version of getByAddress that takes a hostname along with the byte array. This helps in associating a specific host with its IP address, which can be handy in more complex network setups. Next, we have getByName. This method is quite important because it resolves a hostname to its corresponding IP address. It's a fundamental part of network communication, allowing us to connect to servers using human-readable names, which are then translated into machine-friendly IP addresses. Moving on, getHostAddress returns the IP address in a textual format, usually as a string like 192.168.11. It's useful when you need to display or log the address in a readable way. GetHostName, on the other hand, retrieves the hostname associated with an IP address. This can be helpful for display purposes or for reverse DNS lookups. The getLocalHost method is a quick way to get the IP address of the local machine. It's often used when your application needs to identify or communicate with itself on the network. Finally, the toString method converts the entire InetAddress object into a string, giving you a human-readable representation that combines hostname and IP address information. All these methods together provide a comprehensive toolkit for managing IP addresses and hostnames within your network applications, tying back to the overall theme of understanding and working with network identities effectively. Today, I want to introduce you to Remote Method Invocation, or RMI for short. RMI is a powerful Java feature that allows us to invoke methods on objects that are located in different virtual machines, possibly on different physical machines. Essentially, it makes remote communication between Java objects seamless, as if they were local. This is especially useful in distributed applications where components need to interact across networks. The key concept here is that RMI handles the complexities of network communication for us. It takes care of object serialization, network transmission, and method invocation, so developers can focus on implementing the logic rather than dealing with low-level networking details. By using RMI, we can build scalable and modular systems where different parts can run on separate servers but still work together smoothly. This ties into the overall theme of distributed computing and how Java provides the tools to make remote interactions straightforward and effective. Now, let's take a closer look at the key components involved in RMI. First up is the RMI registry. This acts like a directory service where remote objects are registered and can be looked up by clients. It's essential because it enables clients to find and communicate with remote objects without knowing their exact location. Next, we have the remote interface. This is a crucial part of RMI because it defines the methods that can be invoked remotely. Think of it as a contract that both the server and client agree upon, ensuring they understand how to interact. Moving on, implementing RMI involves creating the remote object class that implements this interface, then registering it with the RMI registry so clients can access it. Together, these components form the backbone of how RMI facilitates distributed object communication, making remote method invocation seamless and transparent. This connectivity is at the heart of distributed computing, allowing us to build scalable and modular applications. Let's consider the organization of a program like this. Is it possible to have these two classes on different computers and still have them communicate? The answer is yes, and one technology that makes this possible is RMI, or Remote Method Invocation. Imagine you have some class on one computer and another class on another. With RMI, you can invoke methods from one class on the other computer as if they were local calls. The process involves calling a method on some class, which then communicates over the network to execute that method in another class. The result, or the object returned, comes back just the same as a local method call. This capability is crucial because it allows distributed systems to work seamlessly, different parts of an application running on separate machines, but still interacting as if they were in the same place. It's a fundamental concept that supports scalability and modular design in modern applications. Remote Method Invocation, or RMI, is a powerful feature in Java that enables a Java object running on one machine to invoke methods on a Java object that's executing on another machine. Think of it as a way for objects to communicate across different systems seamlessly. This capability is really important because it lays the foundation for building distributed applications where different parts of a system can work together over a network. Essentially, RMI allows a Java program on one machine to invoke methods on remote objects as if they were local. This transparency makes it much easier to develop scalable and flexible applications that span multiple computers. So, in the context of our overall theme, RMI is a key tool that helps us achieve distributed computing in Java, making our applications more versatile and interconnected. All right, let's dive into the basic RMI process. First, when we're talking about marshalling parameters, we're referring to the process of serializing the parameters so they can be transmitted over the network. It's like packing up the data to send it across. Conversely, unmarshalling parameters is about deserializing, or unpacking, that data once it arrives so the server can understand it. Next, the client object needs to find the correct remote object to communicate with. It does this by looking it up in a registry, which acts like a directory of available remote objects. Once the client has located the object, it marshals the parameters, preparing them for transmission. On the server side, the server object receives the incoming data and unmarshals its parameters to interpret what the client is requesting. Then, it performs its computation or processing based on those parameters. After completing its task, the server marshals its response, ready to send it back to the client. Finally, the client receives this response and unmarshals it to understand the result. This entire process is fundamental to how remote method invocation works, allowing seamless communication between distributed objects across the network. Let's take a closer look at the general RMI architecture. First, the server must bind its name to the registry. This step is crucial because it makes the server discoverable by clients. Next, the client looks up the server name in the registry to establish remote references. This lookup process allows the client to find and connect to the server remotely. Once connected, the stub on the client side serializes the parameters and sends them to the skeleton on the server side. The skeleton then invokes the remote method, processes the request, and serializes the result back to the stub. This entire process enables seamless communication between the client and server in a distributed environment. Let's walk through the process of how remote method invocation works, focusing on the roles of the stub and skeleton. When a client invokes a remote method, the call first goes to the stub. Think of the stub as the client-side proxy. It acts as a stand-in for the actual remote object. The stub's responsibility is to package up the method call, including all necessary parameters, and then send this information across the network. Next, the stub opens a socket connection to the server-side skeleton. This step is crucial because it establishes the communication channel between the client and server. Once the connection is set, the stub marshals the object parameters, meaning it serializes or prepares them for transmission, and forwards this data stream to the skeleton. On the server side, the skeleton takes over. It contains a method that listens for incoming remote calls. When it receives the data stream, it unmarshals the parameters, essentially deserializes or extracts the data, and then invokes the actual implementation of the remote object. This collaboration between the stub and skeleton is fundamental to enabling seamless remote communication, connecting the client's request to the server's response. It's a core concept in understanding how distributed objects work efficiently behind the scenes. Let's take a moment to talk about support for the interface. When we discuss support, we're really focusing on how users can effectively interact with and navigate the system. This includes things like intuitive design, helpful prompts, and accessible features that make the user experience smooth and efficient. A key point here is that good support isn't just about troubleshooting when things go wrong. It's also about guiding users so they can get the most out of the system from the start. That means clear instructions, responsive help options, and a design that anticipates user needs. Connecting this to the overall theme, supporting the interface ultimately enhances user satisfaction and adoption. When users feel supported, they're more likely to trust and rely on the system, which is crucial for its success. So, in essence, strong interface support bridges the gap between technology and user, making the entire experience more seamless and effective. Let's take a closer look at the interface support layers. First, we have the stub or skeleton layer. This layer is responsible for managing the remote object interface between the client and the server. Essentially, it acts as a bridge, ensuring that method calls on the client side are correctly routed to the server. The stubs and skeleton code are generated using the RMIC compiler, specifically with the command rmmic v12 followed by the name of the implementation class. These generated classes are then incorporated into the RRL, or remote reference layer, to facilitate communication. Speaking of the remote reference layer, this layer plays a crucial role in managing the liveliness of remote objects. In other words, it keeps track of whether remote objects are still accessible and active. It handles the communication between the client and server, as well as between the virtual machines. This layer ensures that messages are correctly transmitted and that the remote objects remain responsive throughout their lifecycle. Together, these layers form the backbone of the remote method invocation process, supporting seamless and reliable communication across network boundaries. They are fundamental to understanding how distributed systems maintain transparency and efficiency in remote interactions. Let's go over some key terminology related to remote objects. A remote object is essentially an object that exists on another computer, outside of your local system. When we talk about the client object, we're referring to the object that makes a request. It's the one sending a message to this remote object. Conversely, the server object is the one receiving that request and responding to it. Now, it's important to remember that roles can easily switch. Each can act as a client or server, depending on the situation. Another important concept is the RMI registry. Think of it as a specialized server whose job is to look up objects by name, helping clients locate the remote objects they want to interact with. And then there's RREMIC, which is a tool, a compiler specifically designed to generate stub classes for the client side and skeleton classes for the server side. These components are crucial because they handle the communication details behind the scenes. Connecting these points to our overall theme, understanding these key terms and tools is fundamental to grasping how remote method invocation works effectively in distributed systems. Let's walk through the steps for developing an RMI system. First, we start by creating the interface, which essentially defines the methods that the remote object will implement. This interface acts as a contract between the client and server. Next, we define a class that implements this interface, providing the actual functionality. Once that's in place, we move on to creating the server process, which hosts the remote objects and registers them with the RMI registry. After that, we develop the client process, which will look up the remote objects and invoke methods on them. The next step involves compiling all the Java files to make sure everything is up to date. Then, we compile the implementation class with the RREMIC tool, which generates the necessary stub and skeleton classes for RMI. Finally, we start the RMI registry, which manages the remote objects, references. To run everything, open a new window and start the server, then open another window for the client. This process ensures that your RMI system is correctly set up, running smoothly, and ready for remote communication. These steps are fundamental to building reliable distributed applications with RMI. All right, let's take a closer look at this slide. Here, we're creating an interface called Hello, which is fundamental in Java RMI. The key point here is that the interface extends remote, which means it can be called remotely across different JVMs. The method getGreeting returns a string and throws a remote exception, highlighting that remote calls can sometimes fail due to network issues or other problems, so we need to handle those exceptions properly. This setup is essential because it defines how clients will interact with our remote object. Remember, the interface is the contract. It specifies what methods are available for remote invocation. Connecting this to our overall theme, designing a clear and robust interface is crucial for effective RMI communication. It lays the groundwork for reliable remote interactions, ensuring our distributed applications work smoothly. All right, on this slide, we're defining our implementation class, which is called Hello Impl. Now, this class extends unicast remote object, which is crucial because it allows our object to be exported as a remote object, making it accessible over the network. It also implements the Hello interface, meaning it provides the actual code for the methods we've defined in that interface. Inside the class, we have a constructor that throws remote exception, but there's no additional action needed here. It's just necessary for remote objects. Then, we have the getGreeting method, which returns a simple greeting message. This method also throws remote exception, which is important because network communication can sometimes fail, and we need to handle those potential issues. Overall, this slide highlights how we create a concrete class that provides the remote method implementations, forming the backbone of our RMI application's server-side logic. It's a key step in connecting our interface to actual functioning code that clients can invoke remotely. Let's take a closer look at creating a server process in Java RMI. First, we start by importing the Java RMI package, which provides the necessary classes for remote method invocation. In our Hello Server class, we define a constant host as localhost, which indicates where our server will run. In the main method, we create an instance of Hello Impl, which is our implementation object that provides the remote methods. Then, we construct a string called RMI object name, which is the URL that will identify our remote object. Here, we use the format RMI / plus the host, and then add hello as the name of the object. It's worth noting that if we omit the hostname, localhost would be assumed by default, simplifying the URL. Next, we bind our implementation object to this name using nomming rebind. This step registers the object so clients can look it up later. Finally, we print a message indicating that the binding process is complete. This confirms that our server is now ready to accept remote calls. Overall, this process highlights the key steps in setting up an RMI server: creating the implementation, defining its name, binding it, and confirming the setup. Now let's take a closer look at the client-side code for our RMI application. The first thing to notice is that we're importing Java, RMI, to access the necessary RMI classes. The class is called Hello Client, and we define a constant host set to localhost, which points to our server. In the main method, we start with a try block because remote calls can sometimes fail, and we need to handle those exceptions properly. The key step here is obtaining a reference to the remote object. We do this using nomming lookup, which takes the URL of the remote object, constructed with the host and the name, hello. This method returns a generic object, so we typecast it to our remote interface, hello. Once we have this reference, we can invoke methods on the remote object just as if it were local. In this case, we call greeting, which retrieves the message from the server. We then print out the message received to the console. It's also important to note the exception handling. If the client cannot connect to the server, a connect exception is caught, and we notify the user that the connection failed, then exit. Any other exceptions are caught generically, printed with stack trace for debugging, and the program exits as well. Overall, this code demonstrates the fundamental process of creating an RMI client, looking up the remote object, invoking methods, and handling potential errors gracefully. This connects back to our broader discussion on distributed applications and how RMI allows us to invoke methods across network boundaries seamlessly. All right, let's walk through the compilation and execution process for our RMI application. First, we compile all our Java source files using the command *Java, which ensures that every class involved is compiled properly. Next, we generate the stub and skeleton files with rremic hello impl. This step is essential because it creates the necessary stub classes that facilitate remote method calls. Then, we start the RMI registry with rmiregistry, which acts as a directory service where clients can look up remote objects. Once the registry is running, we launch the server with Java Hello Server. This server hosts our remote objects and registers them with the registry. Finally, the client connects to the server by running Java Hello Client. It's important to note the files involved on each side. On the client side, we have Hello Client class, Hello class, and Hello Impl stub class, which are all needed for the client to communicate properly with the server. On the server side, we have Hello Server class, and Hello Impl class, which contain the server implementation and the remote object logic. This sequence highlights the key steps in deploying and running an RMI application, emphasizing how the compilation, stub generation, registry setup, server startup, and client invocation all come together. It's a practical example of how remote method invocation works behind the scenes, tying into the overall theme of distributed computing and remote communication in Java.